Hi everyone, the topic is network maximum flow algorithm, Edmond Karp method. So Edmond Karp is a BFS based implementation of the Ford-Wilkerson algorithm used to find the maximum flow in a network, in a flow network. Okay, what is the difference between Edmonds and Ford-Wilkerson? So here in Edmond Karp using BFS concept to find the shortest path, then in this shortest path, which one is the minimum capacity, choose that capacity and update the residual graph. Okay, so first step is initialize set flow on every edge as 0. Initially no flow in the network and find the augment path using BFS concept from the source to sink. Okay, use one queue and update the parent node also. Then BFS guarantees the shortest path. So if no path exists, then stop the procedure. Now after find the shortest path, then find the bottleneck capacity, minimum capacity of all the edges. Which one is the minimum capacity of all the edges in the corresponding shortest path, and augment the flow, then update the residual graph. Just subtract this minimum capacity value from the original capacity available in the network. Then repeat this procedure. So if we found next shortest path means, then perform these all things again. If no augmented path is available, then stop the procedure. Compute the maximum force. Simply add the minimum capacity of all the augmentation paths. So all the augmentation, then simply add all the minimum capacity. You find the maximum flow of the network. So this take us on example. Okay. So using BFS concept, what is the source node here? That is 0 is the source node. So we start from the source node 0. Okay, then simply add that source node into the queue, right? So initially the queue contain only one node. So pop out. So the 0 is pop out from the queue. After pop out the particular node, then add the child of the popped node. So here 0 have two children, 1 and 2, then simply add that children in the queue. Then update the parent node also. So is the parent of 1 and 2? So parent is 0, right? Okay. Then the next node is 1. So now the queue contain, the first node in the queue is 1, then popped out from the queue, then simply add the children of 1 in the queue. So 1 have 2 children, so 1 is 3, another 1 is 2, then 2 is already available in the queue, then simply add 3 here. So is the parent of 3, parent of 3 is 1. Okay, then next node is 2, popped out from the queue, then add the 2 children in the queue. To have 2 children, 1 and 4, 1 already processed, so simply add 4 inside the queue. Then update the parent node, parent of 4 is 2, right? Then what is the next node? Next node is 3, then pop out from the queue, then add the children of the node 3. So here 3 have only one children, that is 5. So simply insert into the queue. Now we reach the source sink node, right? Destination. Then stop the procedure. We trace the path from reverse. From destination node we trace the path. So start from 5, then update the parent. So who is the parent of 5? That is 3. After pop the node 3, he had the 5, right? So the popped node is the parent of the added node, new added nodes. Clear? Okay. Then who is the parent of 5? So the parent of 5 is 3 here, right? 3. Then move to 3. Who is the parent of 3? Parent of 3 is 1, right? Parent of 3 is 1. Then move to 1. So parent of 1 is 0. So likewise you trace the path. Okay, so now the first shortest path is 0, 1, 3, 5. Then check the capacity of all the edges in the particular path. Okay, what is the capacity? 0 to 1, that is 16. 0 to 1, 16. 1 to 3, 12. 3 to 5, 20. So which one is minimum? 12 is minimum, right? So the augmented flow of this particular path is 12. Then we update the path like subtract the minimum capacity value from the available capacity. So 16 minus 12, already given capacity. So 16 minus 12, the available capacity is 4 here now. Then 12 minus 12, that is 0. Here 20 minus 12, 8. 8. Okay. Likewise, you update the capacity in the particular path. Okay. Then move to the next augmentation. So the updated capacity is 40, right? 408, right? So the updated capacity is, here the updated capacity is 408. Okay. Then move to the next augmentation. Here start from source, the same procedure. So the source node is 0 here. Initially the queue contain only one node. So pop out from the queue, then add the children of the node 0. 2 node is there. 2 node have the capacity 1 and 13, right? So simply add these 2 node in the queue. So parent of 1 and 2 is 0. Update the parent node also. So then pop out the initial value, pop out the top value in the queue. Okay, so that is 1. So after popped out the particular node, add the children of the corresponding node in the queue, right? So once children is 2 children is there, 1 is 2, 1 is 3. So we cannot add 3 because the available capacity is 0, right? So we cannot add this child node inside the queue. We simply add 2 only, but 2 already available in the queue. So in this step, no need to add any child here. Okay. Be careful, if the particular edges contain 0, we cannot add that node inside the queue. Clear? Then 2 is only 2 is available in the queue. So popped out from the queue, then add the children of 2. Here 2 have 2 children, 1 and 14. So 1 and 4. So 1 is already processed, right? So simply add 4 here. Then who is the parent of 4? 2, right? Then so 4 is popped out from the queue. Then add the children of 4. Here 2 children is there. 1 is 3, 1 is 5. So simply add here 3 and 5. But now reach the source vertex, right? So the parent of these two node is 4, right? Parent of this 2 node is 4. Then now we reach the sync node 5, destination node 5. Then stop the process. Trace the path from destination node, sync node. 5 is destination. Who is the parent of 5? Thus parent of 5 is 4, right? Parent of 5 is 4. Then move to the 4th node. So who is the parent of 4? So parent of 4 is 2. So parent of 4 is 2. Then move to the node 2. So parent of 2 is 0. So reach the, so here the source node. So likewise it trace the path. Then update the, so then check the all the capacity of the particular shortest path. Okay. So 0 to 2, what is the capacity? That is 13, right? 13. 2 to 4, that is 14. 4 to 5, that is 4. So which one is minimum? 4 is minimum, right? So here the augmented flow of this particular path is 4. So already what is the, in first augmentation the minimum capacity is 12, right? So minimum capacity is 12. In this step the minimum capacity is 4. So now add 12 with 4, here 60. Now the maximum flow is 60. Right? Simply add the minimum capacity of each augmentation steps. So now the maximum flow is 16. Then update the recital graph based on the minimum capacity value. Then here 13 minus 4, the value is 9. And 14 minus 4, the value is 10 here. And here 4 minus 4, 0. We cannot use this edge further. So likewise update this graph. Clear? Okay. Then move to next augmentation. What are updated weights? Just update the weight. Here, so what is the weight? Here the minimum capacity initially is 12, right? So here updated is 4. Here 0. Here 8. In second step the minimum is 4. So 13 minus 4 is 9. Here 10. Here 0. So now the two edges with the capacity 0. So we cannot use these two edges. further. Clear? Okay. Then start from the source node. What is the source node here? 0. Then pop out from the queue. Then simply add the child of the node 0. Here 2 children is there, 1 and 2. Simply add 1 and 2 in the queue. So the parent node is 0. Then pop out. So 1 is pop out from the queue. Then simply add the parent of 1. So child of 1 in the queue. So already the 0 is 1 have 2 children, right? 2 and 3. We cannot add 3 here because the capacity is 0. The 2 is there. 2 is already available in the queue. So next pop out the value 2 here. Okay. So now to have only one children, right? 4. So simply add the children in the node. So update the parent node also. The parent of 4 is 2, right? Then popped out 4 is popped out from the queue. Then simply add the children of 4. So 4 have 2 children, 3 and 5, but we cannot add this child because the capacity is 0. We only add 4. We only add 3 here. Okay, add 3. Then parent of 3 is 4. Then 3 is popped out from the queue. Then add the child of the node 3. The child is 5, right? So simply add 5 in the queue. Now reach the destination node, sim node. That trace the path from destination node 5. So here parent of 5 is 3, right? So parent of 3 is 5. Parent of 5 is 3. Then move to 5. So move to 3. Parent of 3 is 4. Then go to 4. Parent of 4 is 2. Then 2's parent is 0. So likewise it traces the path, right? So these are the parent node. In programming wise, you separately maintain one visited array and also the parent array. Okay, these are the parent node. Okay, so now the path is, the third path is 0 to 2, 2 to 4, 4 to 3, 3 to 5. Then update the and then find the minimum capacity of this particular node. So 0 to 2, the capacity is 9. Then 2 to 4, the capacity is 10. So 9, 10. Then 4 to 3, the capacity is 7. Then 3 to 5, the capacity is right. So which one is minimum? 8 is minimum, right? So augmented flow of this particular path is 7. So already we have the maximum flow 16, right? 12 plus 12 is the minimum capacity in the first augmentation. So then second augmentation minimum is 4. Then third minimum is 7, right? We add those all things. Then now the maximum capacity of the network is 23. Then update the graph also. Okay. So here 9 minus 7, that is 2. Here 10 minus 7, that is 3. Here 7 minus 7, that is 0. Here 8 minus 7, that is 1. Okay. Then check once again any more path is available here. Okay. The final updated is 401. What is the final updated? 4. Here is 4. Here 0. Here 1. And here 2, 3, 0. Here 2, 3, 0. So here 0, right? Here also 0. Here. Then any more path is, just check in the graph any more possibilities there to form the path from source to sink. So here we try this 0 to 1, 1 to, so we cannot move here. So 0 to 1, then 1 to 2, so 2 to 4, so we cannot go here, right? Because 0. But we cannot go here also. So no more path is available. Then stop the procedure. So what is the maximum flow of this particular graph? The first minimum capacity 12, second minimum capacity is 4. Third minimum capacity is 7. So total maximum flow in the given graph is 23. Clear? So this is the procedure behind the Edmond Karp algorithm using BFS concept maintained on Q and also parent array. Clear? So Edmond Karp guarantees always fix the shortest path using BFS. It's the meaning. Shortest path using BFS and choose polynomial time complexity. So the time complexity is order of E into E square. So BFS with a Q find the shortest augmented path. Then parent array stores in PFS tree to reconstruct the path. Trace out the path using the parent array. And bottleneck, find the minimum capacity of the edges available in the particular path and update the flow and residual capacity. Repeat until no path from source to sink exists in the residual graph. Clear? Thank you.